Good morning, students. Now we are going to the fourth class of this group theory, that is third sem of 2Bsc for the academic year 2020-21 of AKNU University. Now we are going to the class 4 in the Unit 1 groups. Previously we have learned 6 theorems. Now we are going to the 7th theorem. That is, the statement is, if G dot is non-empty set, then G dot is group if and only if the first bit A, B into C is equal to A into BC. The second bit AX equal to B, YA equal to B have unique solutions in G for all A, comma B, comma C in G. Okay. Here G dot is a non-empty set, and then we want to prove that a necessary and sufficient condition theorem is here. That is, if G dot is group, then we have to prove these two bits. If these two bits were satisfying, then we have to prove G dot is group. Now we are writing that it is in the another form. This question may be asked in the university question paper in the another form, that is, a non-empty set G dot is group if and only if Ax equal to B, comma Ya equal to B have unique solutions in G. It is the most familiar question in the university question paper. It is most important theorem. A non-empty set G dot is group if and only if Ax equal to B, the equations Ax equal to B, comma Ya equal to B have unique solutions in G. Okay, right? First of all, I am writing that given. What is that? Given G dot is non-empty set. G dot is non-empty set. It means here we are writing here like G comma dot in the algebraic structure means binary operation dot is exist in G. That means closure law exists in G is given in this set. This is a non-empty set and existing binary operation. That is like that. What is necessary condition? First of all, we have to take G dot is a group and we have to prove these two bits. That's why I am taking that. Suppose G is a group and for A, comma B, comma C, for any three elements in G. Okay, what is the definition of group? We know that group means four laws are satisfying. What are they? Closure law, associative law, identity law, inverse law. Okay, right. We have to prove these two bits. Those are the first bit is AB into C is equal to A into BC, and the second one is AX equal to B, YA equal to B have unique solutions. If you observe that the first bit is the associative law, is it right? Given that G is group means associative law exists. That means first bit is over. First bit is very clear. That's why we have written in the proof that students kindly follow the cursor. If you go to the first bit, by associative law in G, AB into C is equal to A into BC. This is very clear. Now we are going to the next bit. That is, first of all, I am taking the equation Ax equal to B. Because A is in G, G is group, by inverse law, A inverse is also in G. A inverse belongs to G. That's why I am multiplying A inverse on both sides. That means A inverse into Ax is equal to A inverse into B. I am applying associative law for this one. That means A inverse into Ax becomes A inverse A into X. RHS is same. What about A inverse A? By inverse law, A inverse A is equal to E. X is same. A inverse B RHS part is same. E into X. E is the identity element. That means E into X gives X only because E is the identity element. X. A inverse B right side as it is. X value is A inverse B. That means X is the solution of the equation Ax equal to B. That means the equation Ax equal to B have only solution. But we have to prove that in the question, if you observe the cursor, uniqueness is there. Ax equal to B have unique solution. The equation Ax equal to B have unique solution. That means it has only one solution. So now we do that uniqueness. That means we have to prove two solutions are not there for this one. This equation has only one solution. I am taking that let x1 and x2 are two solutions of this equation X equal to B in G. That means x1 is satisfying the equation x equal to b. That means x1 is equal to b, and the x2 is also satisfying this equation because it is a solution. That means x2 equal to b. We have written here x1 is equal to b, x2 is equal to b. Ax1 is equal to ax2. Ax1 is equal to b. What is b? Ax2. Instead of b, I am writing ax2. Ax1 is equal to ax2. By left cancellation law, a will be cancelled. Then what happens? x1 is equal to x2. We are taking two solutions, but those two solutions are equal. That means the equation x equal to b has unique solution in G. Similarly, we prove that y equal to b has unique solution in G. All the students have to complete this another equation. By taking this another equation, you have to prove the that equation has unique solution. Similarly, as done for the x equal to b equation. Okay, students. Therefore, we say that x equal to b and y equal to b have unique solutions in G. The necessary condition is over. What about the sufficient condition? That means sufficient condition means we have to take that these two conditions are these two conditions. That means we have to take these two conditions and we have to prove G dot is group. For that, I am going to the next step. And in the sufficient condition, I am taking these two bits. You observe that the two bits are taking. Suppose 1 and 2. What you have to prove is G dot is group. Group means we have to prove 4 laws. Those are closure, associative, identity, inverse. And now I am proving all this. What first one is closure law. Since by algebraic structure G dot, that means I have already told you that G dot, this algebraic structure shows that dot is exist in G. That is, this binary operation exists in G. That means closure law exists in G. This represents closure law exists in G. So closure law is over. Associative law. If we go to the supposition, the first part is the associative law, is it right? Associative law exists in G. It's very clear. Then we are going to the identity law. We have a for a comma b in G, x equal to b, y equal to b have unique solutions in G. This is the second bit in our supposition. I am using this second bit. X equal to b, y equal to b have unique solution. When a comma b belongs to G. When a comma b belongs to G. Now I am taking that a comma a in G. I am writing a instead of b in these equations. Then what happens? Ax is equal to b, b replaces a, and ya equal to a have unique solutions. Ax is equal to a, ya is equal to a. That means ax is equal to ya. Ax is equal to ya. Is it right? But if we observe that ax is equal to a means x replaces e. Is it right? ae is equal to a. That means x acts as identity. Is it right? A comes outside a as this. That is, x is called identity. Therefore, x is equal to e. X is equal to e. That means e is identity element in G. Therefore, identity law exists in G. We are going in the inverse law. For an element A, I am using the second bit, same second bit term I am using. That is, x equal to b, comma, y equal to b have unique solutions in G. Okay, right. Now I am going with the two elements a comma e in G. Previously I went with a comma a. Now I am going with a comma e in G. The equations converted as ax equal to b. B replaces with e here. If you observe that a comma b is not there, in the b replaces e. That means ax is equal to b means e. Y equal to e means b. Sorry, y equal to b means b replaces e. That means ax equal to e, y equal to e has unique solutions. In these equations, we are taking a comma b in G. For this a comma e, that means a, b replaces e, ax is equal to e, y is equal to e have unique solution. That means ax is equal to ya, x is equal to ya. If we observe that, let the solution is x is equal to y is equal to c. I am taking that solution is the same as c. That means x and y is equal to c. AC is equal to E, CA is equal to E. That means AC is equal to CA is equal to E. A multiple with C gives the answer E. That means C is inverse of A. C multiples with A on left side, That means C is left inverse of A. Here C is right inverse, here C is left inverse. That means C is inverse of A. That means an element A has inverse C. That means inverse exists in G. We have proved closure, associative, identity or inverse laws. That means G dot is a group. That the sufficient condition was proved. So the theorem is proven in these two conditions are proved now. Now we are going to the another theorem, that is theorem number 8. A finite semi-group satisfying cancellation laws is group. For that, I am taking that a finite semi-group. We know that semi-group means it's satisfying only two laws. What are they? Closure law and associative law only. Now I am taking a finite, that means countable number of elements is there in that set. I am taking G is equal to A1, A2 and so on, An is a finite semi-group with n distinct elements. Distinct means different. That means no two elements are equal in this one. A1 is not equal to A2, A2 is not equal to A3, A3 is not equal to A4, An is not equal to A1, A2 is not equal to An. Whatever it may be, any two elements are not equal. That's the meaning. Distinct means. And G holds cancellation laws. And taking that G is a finite semi-group with n number of elements and it has cancellation laws. I want to show that it is group. I want to show that G is group. G is semi-group means closure associate exists. We want to show that G is group. That means it must satisfy another two laws. Those are identity law and inverse law. Now we prove these two laws in this one. Now, for an element A in G, I am taking A is an element in G. A1 is in G, A is in G. By closure law, AA1 in G. Similarly, AA2 in G, AAN in G. AA1, AA2, and so on, AAN belongs to G by closure law in G. Because G is semi-group. Semi-group means closure associated exists. Closure law like this, I am using closure law here. So I have doubt that is there any two elements are equal? Just I am taking that if possible let any two elements, any two different elements are equal. That means AI is equal to AJ for I is not equal to J. That means suffixes are not equal. If I is 1, then J is not 1. That is 2 or 3, whatever it may be. Here we observe that we have taken in numerics A1 is equal to AA2 like that. This is like that. AI is equal to AJ. By left cancellation, A is cancelling. Then we get AI is equal to AJ. AI is equal to AJ. That means two A's are equal. Two different A's are equal. I is not equal to J. That means these two A's are different. Two different are equal. But we say that in the set, all these A's are different. But here equal. That means we get a contradiction. That G has n distinct elements. G has n distinct elements. Contradiction we got. That's why any of these two elements, AA1, AA2, AN, are all different, and any of these two elements are not equal. That means all are different. AA1, AA2, and so on, AN are all how many distinct elements? N distinct elements in G. We have A's are n distinct. Now we got AA1, AA2 are n distinct elements. Now by using pigeonhole principle means each and every object collects only one image if it has the capacity of 1. That means I easily explain you. That means most of the people, that means all the students are very much interested in the movies. If you go to the movies, there are number of chairs. That is countable number of chairs are there, and countable number of tickets will be given, and that those people who are going to the to watch the movie. That means if you went to the movie, that means the object is chair, and the element is audience. That means you is the element and chair is the object. That means chair takes only one element. That means in each chair there is only one audience will be sit there. In one chair there is no chance to sit two audience. That means only one element occupies one chair. One chair, that means one object occupies one element. That means one element occupies one chair. Is it right? One chair takes only one audience. That means one audience can sit in one chair. Is it right? Like that, object is said. One object has a capacity of taking one element. That means one element must fulfills only one object. Okay? This is the pigeonhole principle. By using this principle, we have n distinct A's are there. Here n distinct AA1, AA2s are there. That means here n objects, here n elements. In these n objects, these n chairs will occupy at only once only. If AA1 sits in A1, then AA2 sits in another seat. The basic fundamental is you can sit in any of the, if a theater contains 300 chairs, then you can sit in any of these 300 chairs, but you can sit in only one chair. Is it right? That is the basic principle that is called pigeonhole principle. Similarly, these are AA1, AA2, AN are there. In that one, these are the audience AA1, AA2, AN. In this one, any one of these can occupy in one place only. Okay? By this principle, every element of G means elements of G means all are S, is in the form of AAI or in the form of AAI. All are converted into in these places. Is it right? Right. For some, B belongs to G because B is in G. We know that all the elements in G are in AA something, AA suffix something. Similarly, B is in G, B is some AAK. For some, AK belongs to G. Is it right? B is in G, all the elements are in G in the form AA something. AK is this is looking like AX is equal to B. X replaces with AK. Is it right? AX equal to B. That means this is the solution. AK is the solution of the equation AX is equal to B, which is unique. We know that from the previous theorem. Similarly, if we prove that A1A, A2A, ANA are all n distinct elements in G, because we have multiplied A here left side for the elements of G, A1, A2, AN. Now similarly we are that A1A, A2A and so on, ANA are n distinct elements in G. Similarly we prove that like this, B is equal to AKA, for some AK belongs to G. Here this is YA equal to B like that equation, YA is equal to B. Here Y replaces AK, that means AK is a solution of YA is equal to B, which is unique. Okay, now we have proved that AX equal to B have unique solution, YA equal to B have unique solution. By known theorem, that is the previous theorem, G dot is a group. What is the theorem? If you go to the AX equal to B, YA equal to B, NX solution implies G dot is a group. This is a sufficient condition, is it right? We have proven these two, that's why G dot is a group in this theorem by using that previous theorem. Hence, a finite semi-group G was taken here, then that is a group. That means a finite semi-group satisfying cancellation clause is a group. The theorem is over. So students, these two theorems are very important. So all of you want to follow regularly because these theorems are also came into the ring theory syllabus also. So you have to follow these very strictly, and I am posting this in the PDF format in your WhatsApp group. So all of you write the notes and show in the next class. Okay, kindly follow it, and if any doubts occur, then we can discuss in the next class. Okay, or you can ask I am stopping the recording, so you can ask me doubts now. If instant doubts are there, if after preparing, if there is any doubts in the preparation, then you can ask tomorrow also. Now we can ask the instant doubts, what it may be. I am stopping the recording.